Hey guys, how you doing? It's Coach Scott here, and well, it's another day and another week, and here we go on to Unit 5, right? We're going to talk about covalent compounds today, right? Covalent compounds. So, let's go back to our little slide where we talk about the different types of chemical bonds. Okay, there's three basic types. We've got ionic bonds, and if you recall, we just studied those in Unit 4. And that's where there's an electrostatic attraction between ions. And these ions will be attracted to each other because of the charges, and they're going to form ionic compounds. Now, that's a very, very, very strong bond. Okay, the next type, what we're going to study in this unit, is what we call a covalent bond. And these are where the valence electrons are shared between the atoms, and they're going to form either what we call network solids or molecules. Okay. Give me a little thing so I can draw a little bit if needed. All right. So use my little highlighter there. So then we also have metallic bonds. We call these metallic bonds. Now the valence electrons, and they're in metals, right? Many metal atoms, they share these electrons across all the other atoms, and we call that a sea of electrons. A sea of electrons in a metallic solids. So, of course, this unit we're going to be looking at covalent bonds. So, let me move this out of the way. How the ionic or covalent bonds depends on the difference in the electronegativity between the atoms, right? The smaller the difference, the more likely the electrons are shared, and then the bond is considered covalent. So covalent is sharing valence electrons. Ionic is they steal the electrons, right? The greater the difference, is the more likely the electrons have been transferred or stolen, if you would, or given up, and the atoms are ionized, and this will create a ionic bond. So let's look at this example. Let's look at the electronegativity differences between fluorine, which is the most electronegative atom, and some of the other atoms. Okay, so the electronegativity of the atoms is shown here in this little chart right there, right? So there's the difference with lithium, and I can fix this just a little bit, but I won't. So lithium is 1, beryllium is 1.6, boron is 1.2, carbon 2.5, nitrogen is 3, oxygen is 3.5, and of course fluorine is 4, all right? So let's look here. So if I got a lithium fluoride bond, all right, then let me go ahead and change this into a pen. So lithium and the fluoride bond, I've got a bond like this. Oop, I don't think I changed it. Pen, and let's do purple. All right, so lithium is got a 1, all right, electronegativity, and fluorine has a 4. So of course that difference will be 3. That's going to be a very strong ionic bond. All right, if you look at beryllium fluoride, well, that's 4 minus 1.6. Minus 1.6, that gives us 2.4. Still above that magic 1.7 difference, right? So this would be a ionic bond. Now we get boron and fluorine, BF. All right, so now we've got put it up here, 4 minus 2, so I get a 2.0 electronegativity difference. Yeah, we're getting close to that 1.7, so that could be considered still a ionic bond. If you look at carbon and fluorine, all right, so there we got 2.5. Carbon goes there, and boron goes there. Yeah, these are a little misplaced here. We'll have to fix those. Right, so carbon is 2.5, so that will be a 4 minus 2.5, or that'll be a 1.5. Okay, 1.5. Now we're getting to where this would be a covalent bond, or those electrons would be shared amongst each other. If you notice, as we get to the right side or into the nonmetals, that's where we're getting those covalent shearing bonds. Nitrogen and fluorine, well, then that's 4 minus 1, or excuse me, 4 minus 3, that gives us a 1, okay, and that's definitely a covalent bond. And then oxygen, 3.5, 4, so that's 4 minus 3.5, that will be a 0.5 difference. Again, covalent. 4 minus 4, of course, that's going to be covalent also. They will share those electrons. So, if we look at this bond character, all right, and we say we use that 1.7, okay, here's one of those little exceptions. It's hard to say that a bond is either totally let's keep it like it is. We can make some simplifications, but there is a spectrum of how ionic, how covalent a bond might be. So, ionic bonds, when the difference is greater than 1.7, we say that is a ionic bond. If it's less than 1.7, we call it a covalent bond. So neither of those electrons are going to be taken, right? They're going to be shared. Now this usually takes place between two nonmetals because that's where you'll have that small difference in electronegativity. All right, so there are two types of compounds that actually share their electrons. The first type is what we call the covalent network. Now these are large compounds, all right? And what they are repeating elemental or molecular units that are covalently bonded together. Now diamond is an example, graphite, quartz, silica sand, right? That's a many silicon dioxides that are sharing electrons. We got models of that we'll look in the classroom, all right? And of course, molecules. Now these are smaller compounds. They're discrete units of one or more elements that are bonded together. And we want to think water is a good example. Water is a good example, or diatomic oxygen or oxygen gas, O2. So H2O and O2 would be molecules because they are sharing those electrons. Now, let's look at these covalent network compounds. Now, so these are ionic and metallic substances, all right? They don't consist of discrete individual molecules. What they do is they form large compounds of networks of covalently bonded shared electrons represented by formula units, right? Just like in ionic compounds. So carbon, there's two main type of solid covalent network for carbon, right? One is diamond, right? If you see there's a carbon atom there, they've got a tetrahedral structure, and each of those carbons will share their electrons with the other one. Now this is graphite, like pencil lead or a dry film lubricant, right? So there you've got a bond on that carbon, a bond on that carbon, and then these are covalently bonded with another carbon up in here. And so you can see that these guys have totally different geometric structures, and that's why they act different. That's why diamond is so strong and graphite is one of the softest materials out there. Diamond is the hardest, right? So, some properties of these covalent network compounds. One, they're non-conductive because they're made up of non-metallic atoms. So they're going to conduct little or no electricity. There's no free electrons to move down there. They're very hard, usually, because they're bonded together. And these materials, of course, tend to be very hard. They all have high melting points, hard, non-conductive, high melting points. Think about diamond, like it's next to impossible to melt that. These covalent bonds are very strong, and these covalent networks have many bonds that will give them high melting points. Okay, so that's just the way they are. Now, let's talk about molecules. So we've talked about two things, covalent networks. Now we're going to talk about the second, molecules, molecular compounds. Now these are different from ionic compounds, and they're different than the network covalent solids in that they have a specific number of atoms. They're discrete structures all by themselves. If you look at water, water has 2 hydrogen atoms and 1 oxygen atom, not a bunch of them, right? It's not just a fixed ratio, all right? There's a specific number of each of those atoms in that molecule. So we've talked about NaCl, sodium chloride. Now it can have a gazillion sodiums as long as it has the same gazillion chlorines, then that ratio is going to be 1 to 1. Now water, okay, not a gazillion. Water has 2 hydrogen atoms and 1 oxygen atoms. That's it. All right, so let's talk about these properties of molecules. So these atoms are held together by strong, here's a new word, intramolecular bonds. Okay, held together, H2O, held together by strong intermolecular bonds. The molecules, though, are attracted to each other by weak intermolecular forces, which we'll study about those in the next unit. So, as a result, they give these different properties than the covalent network compounds. All right, they are non-conductive because they're made up of non-metallic atoms, but these molecular compounds are excellent insulators. Most of them have not low melting points. The molecules are very small. They're held together by weak intermolecular forces. They're not bonds, and these are very easy to break. So this is a bunch of water right here, right? So those dotted lines represent the intermolecular forces. The intramolecular forces is these 2 hydrogen atoms being held together to that oxygen atom by the intramolecular forces, the ones inside the molecules. All right, so yeah. So this is a really fun unit. It's a very busy unit. We talk about a lot of things, but guys, I think we'll have fun with this. This is good. Right before the semester break, we can get this done. So anyway, this is Coach Scott saying have a great evening and peace out.